Welcome back, everybody. It is Bunsen Bernie once again, here from my personal science lab. And today, we are under pressure. I always feel like I'm under pressure with you guys. Gotta keep you happy. But today especially, we're gonna be doing some pressure demonstrations. So we've got some really cool stuff lined up. You can see it barely fits on my counter. That's how many demonstrations I have for you guys. So we're gonna let a couple more people file in here. I already see you popping in. Gonna get the safety goggles on. All right. So again, we'll let a couple more people file in here. Welcome, welcome. Love to see everybody joining us. Thanks again for joining us, for supporting the Science Center. Once again, I am Bunsen Bernie live here in my personal science lab. So today we're going to be talking all about pressure. So we're going to be talking mostly about air pressure. So we can see going on right next to me, I've got a balloon here. And no, there's no magic, no tricks, no strings attached. It's not taped to the ceiling. There's nothing attaching it to that. So you can see nothing to tangle me up here. But what you can see is there's a fan right here underneath it. And I'll move this stuff out of the way so you get a little bit of a better view. You can see there's a fan underneath it. So this is what we call a Bernoulli blower. So a Bernoulli blower uses the Bernoulli principle, which says that a fluid, in this case air, as it moves faster, it decreases in pressure. So that fast-moving air that's going up from the fan has a lower pressure than the air around it, which has a higher pressure. And that keeps it in place here. So if I turn the fan up, we can see that balloon is elevated even higher, almost out of the camera angle here. And then if we turn this down, oh, that's even higher. So we'll turn this down one more. And we can see it's back at that nice steady level. Now what's really cool about this, we can direct the airstream. So if I use my hand here and turn the fan up a little bit more, I can direct that airstream to allow the balloon to move to the side. Isn't that awesome? So it's not even over the fan right now. You can see the balloon's way over here. We've got the fan over on this side. And as soon as I remove my hand, just like that, it's gone. Alright, so again, that is the Bernoulli principle. So that tells us that the faster the air is moving, the less pressure there is going to be. And if we have a slower moving column of air, it's going to give us a higher pressure. Now, what we can do is do this on a smaller scale. So we can do this with a smaller blower. And I've got over here, just out of sight, a ping pong ball. And what I'm going to do is turn on this blower. And you can see even turning it sideways, it still works. To a certain angle. So we are going to check out some other pressure demonstrations. So I've got a can of Coke here. No, I wasn't drinking this morning. What we actually are going to do, we're going to heat up this can of Coke. So I'm going to come back here to the stove, and I'm going to wipe that down. There's a little bit of water on there. So I'm going to wipe that down, and then I'm going to turn on the stove to high, and we're going to let that water boil for just a little bit. So as that water boils, the pressure inside of the can is going to decrease. So what's really awesome about atmospheric pressure is that we don't really feel it. But if we were to take a measure on just 1 square inch, that's more of a circle, but 1 square inch, imagine 1 square inch column of air, all the way from the ground up to space. So about 60 miles of air in that 1 inch column. That would weigh about 14.6 pounds. So over 14.5 pounds in that 1 square inch. Now normally we hear of this as PSI, pounds per square inch. So 14 PSI, or 1 atmosphere, is the pressure that we feel from all of that air on our bodies here on Earth. Now, the square inches on that container, on our soda can there, square inches are about 70 square inches on that container. So normally atmospheric pressure is pushing down with over 900 pounds of pressure. Now, because the soda can is already open, it does not feel that pressure from the outside, because that pressure is also pushing from the inside. But what we're going to do, we're going to change that. So I'm boiling the water there, and again, that's going to decrease the pressure of the air inside of the can. And it's going to do this by pushing out all of the air as it heats up. As we know, heat rises, and it's going to escape from that can. So I'm going to take that can once we start to see it boil, and I'm making sure to keep an eye on it because it is on the stove. So I'm making sure to keep an eye on it, but I'm going to grab it off of there, and then I've got an ice bath here prepared. And in this ice bath, I'm just going to dump that can right into here. Now, something really interesting about water. It is incompressible. So what that means is we can't build up extra pressure with water. Well, you say, Bunsen Bernie, I have one of those little garden sprayer things that you have there. And when I squeeze the air in there, it builds up pressure. And then it shoots the water out. You are absolutely right. It does build up pressure, but it does not build up pressure in the water. It's merely squeezing the air that is around that water. So if you look at these, it tells you there's a max line there, and the reason for that is you need a little bit of air to be able to compress. If we try to compress the water, bad things happen. We can break our container if we are trying to compress that water. So we've got air inside of here, and if I squeeze this down, you can hear it releases that air. So what we did there was the opposite of what we're doing with our soda can here. With the compression here, we're adding more molecules of air inside of here. And when we add too many molecules, they're jammed up in there. Now, the universe likes equilibrium. It likes things to be equal. If the pressure inside of here is greater than 14 psi, if it's greater than the atmospheric pressure around it, it wants to drop down to that normal atmospheric pressure. And it's going to look for the easiest way out. And of course, that's going to be through this nozzle when I push down here. So greater pressure in here, less pressure on the outside, and it wants to escape. We're going to try to do the opposite of that in a little while with this really cool contraption here. So I'm going to grab a pair of tongs, and I'm going to get our soda can. So we can see our soda can is boiling. Maybe you can't see it back there, but trust me, it is boiling. There's steam coming off the top. And I'm just going to grab this very carefully. So maybe you can see a little bit of that steam coming off of there. And as I place this upside down in here, we can see that can has been crushed by those 900 pounds of pressure that are pushing down on it from the atmosphere. So that's a really cool, really simple demonstration, and you saw it took me less than 5 minutes to get it all rigged up. Just a little bit of water in there, heat it up, place it upside down in a bath of water and ice. So what happened there, again, we had that air escaping from here, and as the air escaped, it needed something to be filled with. Now we placed it in here, and as we cool it down, that gas started to contract, and it started to pull in. It took up a lot less space inside of the container once it cooled down. So to get it to cool down very quickly, we use that ice bath there. So that is our soda can demonstration. I'm just going to get this out of the way before I spill it. All right, awesome. So inside of this container, there's a little bit of isopropyl alcohol. I only put a little bit. I know it's pretty scarce these days, so I want to be sure that I'm using just the amount that I need. And on top of this container, there's something called a soda saver. So this is something that you can find readily available, and this is just a used 2-liter bottle. So a little bit of isopropyl alcohol in there, and as I'm adding air to this, what do you tell me in the comments? Am I increasing the pressure by adding more air in there, or am I decreasing the pressure by adding more air in there? All right, so I'm going to continue adding it, and think about it. Those air molecules, they're getting closer and closer together because there are more and more of them in there. All right, I see some thumbs up, and I believe that means that we are increasing the pressure, and you are absolutely correct. Good job, Selena. We are adding pressure. All right, so we can see here, we've increased the pressure in here, and it's really hard to squeeze now. Now, if we let all of that pressure out by opening this top here, it's going to decrease the pressure in there. Now, alcohol has a very, very low boiling point. It's highly volatile, which is why it has that strong smell to it. Even at atmospheric pressure, those molecules are jumping off all over the place. And what we can do here is make that happen very, very quickly by decreasing that pressure. So I'm going to try to get the best lighting here for you. Maybe if I move this light over a little bit. Okay. So got some good lighting there, and we'll just pop this open. And just like that, we created a cloud in a bottle. So that decrease in air pressure allowed the gases inside of here to expand very quickly. So I'll close this off so we can hang on to our cloud. And that's exactly how clouds are created. So not quite as fast, obviously, but that is how they are created. So there's a decrease in pressure. If we go higher up into the atmosphere, there's less air above us pushing down, and it's not going to be quite 14 pounds per square inch pushing down on us, depending on how high you go up in the atmosphere. All right, so we'll get that out of the way. We'll move on to one of my favorite experiments here, and that is our vacuum chamber. So I'm going to grab a balloon here. And I'm just going to fill this up a little bit. So not very much here. And I will warn you, this does get a little bit loud. About as loud as our air blower here. But what I'm going to do, I'm going to take our balloon and place it inside of our vacuum chamber. Now, with our cloud in a bottle, I was adding molecules in there. I was adding air molecules in there. So you remember I said we were increasing the pressure, or actually you told me we were increasing the pressure. Now what we're going to do, we're going to take that air out of there. And this requires some immense energy. So I've got a really big vacuum pump down here. Oh, it really is heavy. All right, so I've got a really big vacuum pump down here, and we're going to go ahead and get that flipped on, and that's going to pull the air out of this container. All right, and as that air begins to escape from the container, we can see that balloon is starting to expand. All right, we can see a little better now. My hose was coming disconnected there. But we can see that balloon begin to expand. And now this container, this lid is stuck on there. So this is a very, very thick container of glass to be able to hold on to all of the pressure that is pushing down from the outside. So remember, there is less pressure on the inside of the container and more pressure on the outside. Alright, so we can turn that off and we can see just how big that balloon is now. It is massive. And it'll continue to grow just a little more as it decreases in pressure. As it continues to decrease in pressure. Now what happens if we add pressure back into the container? What do you think is going to happen to that balloon? Let's find out. So we're going to release the vacuum. And we can see that balloon shrinks back down to its original size. Isn't that awesome? Alright, don't forget to drop your questions in the comments if you have any. I'm not done yet though. We have some delicious treats to put inside of our vacuum container. We've got some jumbo marshmallows. So I've got a marshmallow here. I'm going to place that in, and might as well go big because I'm already home. So we're going to add 5 marshmallows in there, and I'll leave a marshmallow out, that way we can see what it looks like compared to the ones that are inside. Alright, so I'll get this clamped back down, that way our vacuum does not release the pressure. And we're going to turn it on one more time. So we can see the original size of the marshmallow here. And yes, it will be a little bit distorted because of the glass. But I can assure you they are growing. They are growing. Oh boy. So they're at least doubled in size now. This one back here is huge. So we can see the original size of the marshmallow over here compared to those marshmallows that are inside. And that is crazy. Alright. Now if we release the vacuum on this one, we'll turn it off and release the vacuum. You'll notice, similar to the balloon, they will decrease in size. But these marshmallows actually go a step further, and they shrink down even smaller than their original size. So we can see the original marshmallow here compared to one marshmallow that we placed into the vacuum chamber. Now you can see how much smaller it is compared to the original one. And the reason for that is there are tiny little air pockets in this marshmallow. And as we pull that vacuum, it pulls the air pockets out from inside of our marshmallow. When we release the vacuum and repressurize our container, there's no place for those air pockets to go back into, and so it compresses it down. So, if you remember last week, my buddy Hydrogen Harry, he was talking all about density. Now, which of these marshmallows do you think is more dense than the other? Do you think it's the one that is smaller, that we just took out of the vacuum chamber, or this larger one here? So which one of these is the more dense marshmallow of the two? Go ahead and drop that in the comments below. Let's see who gets that one right. All right. So we're going to take these marshmallows out, and I'm going to get some warm water for this next experiment. So if you'll excuse me as I go to the sink and grab some warm water. Now for this experiment, it's important to have warm water. And the reason for that is, as the pressure decreases, it's going to allow those molecules, which are already moving fast because they are warm, it's going to allow them to move even faster and spread even further. And if you watch our demonstration about solids, liquids, gases, plasma, you'll know our liquid, when those molecules start to move even faster, turn into what state of matter? Go ahead and leave that one in the comments below as well. All right, so I've got some warm water here, and I'll probably have to bring you a little bit closer for this one. So the more dense of the two marshmallows is going to be this little one here. So although it is smaller, it takes up less volume, the same mass is there. So this marshmallow and this marshmallow, if we weighed them, they would still weigh the same amount. But this one has it in a much more compact container compared to this one after coming out of that vacuum chamber, because we've gotten rid of those gas bubbles that are inside of there. Okay, so I'm going to bring you a little closer for this one. All right, how is that there? So hopefully you can see inside of that container really well. I'll turn it just a little more. And I'm going to turn this back on. So remember, it's going to get loud. Okay, so I've sealed off my container, and you can see it starts to get a little bit foggy in there, and the reason for that is those gas molecules coming off of the liquid. Now, if we leave it long enough, there's not going to be enough pressure pushing down on those liquid molecules, and what that's going to allow is for that water to boil. Alright, so I can see a couple bubbles forming in there already. So this vacuum, it's not a vacuum cleaner, but it is to allow us to simulate experiments in a vacuum. So the vacuum of space, we can see the bubbles going there. And I'm going to take you off the mount here just for a moment. That way you have a better view. Okay, so we can see that water is beginning to boil. So that water is boiling because we've taken all the air from around it and we've removed it. So as we remove that air from around it, it allows it to increase the amount of molecules that are moving, and of course it decreases that pressure. So again, you can still see it boiling in there. So as we turn this off and put the air back in there, gonna need the pliers for this one. And you can hear that air being pulled in. Very strongly there. And now, of course, it's humid air because the water. And this water, although it was just boiling, I can put my finger in it. It is perfectly safe to touch. So again, from boiling back down to room temperature in a matter of seconds. So the boiling in this case was not coming from the heat, it was coming from the lack of pressure inside of the vacuum chambers. Alright, so unfortunately that is my final experiment there. Again, if you do have any questions, make sure to drop those in the comments below. That's always my favorite part. Answering questions, imparting knowledge, hopefully helping somebody learn something new. Okay, and I see Laura answered there correctly. The smaller one was denser. Yes. Okay. So I'm going to check the iPad here to see if I have any other questions. Alright, and it doesn't look like any questions are coming in just yet, but we'll give it a minute. Alright, I'm glad you enjoyed that experiment. You are very welcome, Laura. I'm glad you enjoyed it. Alright, do we have any requests for our vacuum chamber? Usually people ask us to put something in there. What happens if you put a soda can in there? Okay. For the sake of science, we're going to find out. So I've got our sparkling water here. I'll take a little sip, and I'm going to get a glass so you can see what it looks like when it's fresh out the fridge. So as I pour this in here, we can see all of those bubbles forming. So we'll go ahead and place that into our vacuum chamber. Alright, and I'll get everybody down here. Why does the glass not shatter? That's an excellent question. So this is very, very thick glass. It's also very heavy. So you can see just how thick the rim of the glass is there compared to something like a glass here. It is extremely, extremely, extremely thick. And it allows that pressure on the outside to build up without crushing it. Okay, so I'm going to turn this on here, and I will get right back to Jennifer's question. Okay, from Jennifer, with the marshmallow in the chamber, does that change the taste or consistency? It does not change the taste, but I will tell you I'm not going to be eating this marshmallow. There is some grease down here at the bottom that we have to place to keep a good seal on our container. So that has gotten on our marshmallow, but it would change the consistency. Not the taste, but the consistency. It will make it more dense. So again, just like that boiling water, where it decreased the pressure in there, we can see it's decreasing the pressure, and it looks like it is boiling again. And what this is doing is removing all of those carbon dioxide bubbles that are inside of there. Now, unfortunately, I don't have a water balloon prepared, and my sink will not allow me to fill a water balloon, but that is an experiment that I'm going to have to try at a later date. Alright, so we can see those bubbles going in the container there. Hopefully you can see them going on right there. And it's removing the carbon dioxide bubbles from the container. Now, if we did this in an enclosed can, it wouldn't really affect the can all that much because the can is rated for that pressure. Does it mess with fruit like a banana? So, if there are air molecules in there, it will remove those air bubbles. It does not make it stretch, though, like the marshmallows that we placed in there. Riley H9 wants to know what happens if you put candy in there. I am sorry, Riley. I don't think I have any candy at home right now. Wait a minute. My wife is telling me we do have airheads. Okay. So I will be learning along with you on this one. I have never tried this experiment with an airhead in there. So we're going to find out what happens. So we're going to get the air back in there. Alright, and now, as we take our sparkling water out of there, it is not so sparkling. So it is really, really flat. All those gas bubbles escaped from the container. So I'm going to get this open and place it inside of here. We'll find out exactly what happens here. So how about we put one open package and one closed package. That way I can eat one afterward. And I'll tell you if it tastes any different to me. Okay. So we've got a closed airhead package and an open one there. We're going to seal this back up and get the vacuum going again. Eggs. What would happen if we put eggs in there? Now, I have a feeling that would be a messy experiment, Mr. Harry. So I'm going to go ahead and say I'm going to take a pass on that one. But I think eggs would probably explode. I might have to try that at another time. And probably not in the personal science lab here. So we can see that airheads container. Let's see if I can lift this a little for you. We can see that airheads container, the one that is closed, the gas molecules in there are beginning to expand. And it's filling up just like our balloon started to expand. It's filling up, and soon enough I feel like maybe it'll burst. Ooh, a Three Musketeers Bar. Unfortunately, airheads are the only candy I have at home right now. If we did put a Three Musketeers Bar in there, I feel like it would work very similar to our marshmallow, as it does have lots and lots of air in it. Okay, so we're going to get ready to remove this. So we'll let the air back in here. Okay. And it doesn't look like it did much, although it does feel a little strange now. It does have that weird texture to it, as if the bubbles that were in there started to come out. We'll open this one up here and see what it looks like. I think that looks pretty good. It is definitely a little harder, though. All right. I want to thank everybody once again for joining me, Bunsen Bernie, live here in my personal science lab. Excuse me. The airhead's in there. Once again for joining me here in my personal lab. I appreciate you guys, every one of you, for joining me. Thank you for all of the awesome questions. I hope you enjoyed all of the experiments today. Don't forget to look for us next week back here on our Facebook page. We'll be coming at you live once again. We're going to be going a little bit earlier next week, so be on the lookout for the time for that. All right. Thank you, everybody. I love you all too. Once again, stay safe, stay healthy, and most importantly, stay happy. Thank you.